Okay, so as we're looking at this one, the integral from 0 to 13 of dx over the cube root of 1 plus 2x squared. So the first thing I would do with this is, because I recognize that this is just a giant pain of a bunch of exponents and roots and a binomial expression inside of it all. What I would normally do with these is I would rewrite it so that there's no longer a fraction. So this is a power of 1 plus 2x to the 2/3 power in the denominator. So I'd make that I would just turn it into 1 plus 2x to the negative 2/3 power times the dx. And then from there, if I could substitute out all of this 1 plus 2x, if I get rid of the binomial, then I've just got a variable to a power, which I can use the power rule for. So at this point, what I would do is I would just say, let's let u equal 1 plus 2x. And if u is 1 plus 2x, then du is 2 dx. I'll put a 1/2 outside and a 2 inside. And I'll make my substitution. So I'll have 1/2 of the integral of u to the negative 2/3. And then we're going to have to change our limits of integration. They'll no longer be 0 and 13. So the 0, 1 plus 2 times 0 makes this 1. So our lower limit will be 1. And then 1 plus 2 times 13 makes our upper limit, our new upper limit, 27. So far good?
Yeah.
Okay. And I forgot my du on that. And then this will just become 1/2 of, and then the integral of u to the negative 2/3 will go up to u to the 1/3, so cube root of u. And then we're going to divide by the 1/3, which is the same as multiplying by 3. It's not from 0, from 1 to 27. Everybody good with that?
Yeah.
So we've got 3/2 times the cube root of 27 minus the cube root of 1, which is 3/2 times cube root of 27 is 3, cube root of 1 is 1. So we've got 3/2 times 2, which is 3. Good, does that make sense or no?
Yes.
What happened to the squared at the bottom?
That's 1 plus 2x to the 2/3 power, to the 2/3 power.
What happened to the 2? To the power 2?
That's what I'm saying. That's 1 plus 2x. It's being raised to the second power, and then cube rooted. So that's a 2/3 power.
Oh.
And so since it's in the denominator, it becomes a negative 2/3 when you bring it to the numerator.
Oh, okay. Thank you.
Everybody good there with 2j? Okay. All right, next question was on 2k. What was 2k?
From 1/6 to 1/2.
Okay.
Cosecant pi x, cotangent pi x dx.
Oh, nice. That's a fun one. All right. So on our rule sheet, we have an integral for cosecant x cotangent x, or cosecant u cotangent u, right? The integral of cosecant cotangent is negative cosecant. Everybody agree with that?
Yeah.
Yes.
Hopefully that's what you should have memorized already. And so if this was just cosecant x, cotangent x, great, then that'd be negative cosecant x. But since there's this function inside of here, since there's this pi x inside of each of these, we need to get rid of that pi x by doing a substitution. So we'll let u equal pi x, and du will be pi dx. And so we'll have to put in a pi inside of here, which is perfectly fine. That's just a constant, right? And we'll put a 1/pi out in the front of it. And so then this becomes 1/pi times the integral. And then now our lower limit was a 6. And so now it should become pi/6. And our our upper limit was 1/2, so now it should become pi over 2. And then the pi dx will become a du. And the cosecant pi x will just be cosecant u. Cotangent pi x will be cotangent u. And so we have this integral. Everybody good with doing the substitution to turn that into this integral?
Yeah.
Okay. So we got 1 over pi. And like we said a minute ago, the integral of cosecant cotangent should be negative cosecant. And we will evaluate that from pi over 6 to pi over 2. So what's the cosecant of pi over 2? 1. Should be 1, so we got a -1 there. So we got -1 minus, and what's the cosecant of pi over 6?
2.
Yep, it should be 2, right? Because the sine of pi over 6 is 1/2, so the reciprocal of that is 2. And we just got this. -1 plus 2 is 1 times the 1 over pi is just 1 over pi. Any questions on that now or no? All right, any other questions from the homework? All right, 2L. What's the next one here? 2L. All right, what was 2L?
The integral from 0 to √3 of x to the 5th times the square root of x squared plus 1 dx.
All right, so this is very similar to the ones we were doing at the end of the day yesterday, right, where we're gonna let u equal what's inside of the square root. So du will become 2x dx, which means we'll have to put in a 2 and a 1/2. So we'll have 1/2 of the integral, and I'm going to keep this all in terms of x for now. We're going to write this as 2x, x to the 4th, and then root x squared plus 1 dx. So the x squared plus 1 will become a u, the 2x dx will become a du, and the x to the 4th, which is x squared squared, will have to become u minus 1 squared by using our original u substitution. So we've got 1/2 of the integral of u minus 1 squared times root u, or u to the 1/2 du. And our 0 to √3 will need to change. So 0 squared plus 1 gives us a new lower limit of 1. And √3 squared plus 1 gives us a new upper limit of 4. Everybody good with that?
Yeah.
Okay. All right, and so then we end up with 1/2 of the integral from 1 to 4, u minus 1 squared. We'll distribute that out and then take the u to the 1/2 through it. I'm going to do all that in one step. The u minus 1 squared's first term is u squared times u to the 1/2 is u to the 5/2. Then we get a minus 2u, so that'll be minus 2u to the 3/2. And then a plus 1, so that'll be plus u to the 1/2 du. And now we just integrate. So this becomes 1/2 of 2/7 u to the 7/2 minus 4/5 u to the 5/2 plus 2/3 u to the 3/2 from 1 to 4. And since this is a definite integral, we don't need to convert back into terms of x. So this just becomes 1/2 of, and then we've got the 4 goes in, so this becomes the square root of 4 is 2 to the 7th power is what was that 2? 128 times the 2 here is 256 over 7. And then this one becomes 32 times 4, which would be 128 over 5. And then this one would become 16 over 3. And then we'd have minus 2/7 when we plug in the 1, minus 4/5, plus 2/3. And I don't know, that comes out to be something when you evaluate it all out. But that's the calculus part, at least. I don't know. I mean, finding the common denominator is probably not a good use of our time. I mean, it's, what is it? It's 105, but it's going to be some unpleasant arithmetic. So does that help? Is that good enough? Yeah. Cool. So we'll just say ... Now, any other questions from the homework? All right, looks like no more questions at this moment on that. So if you have any other questions on it, just let me know tonight before tomorrow's quiz. I'll be happy to help you go through whatever problems you might have. We will have a quiz tomorrow on just integrals. So there'll be some where you just need to have, you need to know the power rule. There'll be some where you need to know all the formulas on that integral sheet. There'll be some where you need to do substitution. So that's that. Good. Hopefully you feel like you are ready for the quiz tomorrow. So we will now move on to what we call the mean value theorem for integrals. And so what this mean value theorem for integrals does is it allows us to find the average value of a continuous function on an interval. So if you think back to, let's see, remember yesterday we were going back in time to like ancient Greece and thinking about Pythagoras. Well, now we're going to not go back quite as far. We're going to go back to when you were in like 2nd grade or something. And they were like, all right, this is how you find the average of something, right? And they said, here are 5 numbers. And you added the 5 numbers up, and then you divided by 5, and you said, that's the average, right? Remember doing that?
Yes.
Yeah, hopefully you remember doing that. They called it finding the average or finding the mean, right? Well, that's accurate. That's what you were doing. You are finding the average of a set of data points. Like if I said I have this data point and this data point and this data point and this data point and this data point, the average of each of those data points was the number that you got. But if instead of taking just the data points, if I took every single value in between A and B for a continuous function, we can use this method to find the average value of the function, taking into account every single instant in time between A and B. So if we have some function that, let's say, models the temperature at a certain, on a certain time interval from noon to 1 o'clock today, we should be able to find the exact average temperature that it was during that 1 hour by using an integral. And so the way that the average value of a continuous function is defined is, it says, find the area underneath the curve on the interval. So find the area from A to B, and then find the height of a line that if I were to extend the line from A to B and make a rectangle out of it, the two areas would be the same. So it's saying the area under the curve is equal to the area of a rectangle of height h that extends from A to B, the same length of our interval. Does that make sense?
Yeah.
Yeah.
So effectively, all we're looking to do is we're looking to make the blue area equal to the red area, right? We want the area under the curve to be the same as the area of this rectangle. So we're going to very quickly develop this mean value theorem for integrals. What is the, if this is the function, let's call this function f of x, which makes this function also f of x. What is this blue area? The blue area should be what?
The integral from A to B.
Right, it's just the integral from a to b of f of x dx, right? And that's what we've been talking about, right? That's what integrals are, okay? And we want that to equal this area in red. Well, what's the area in red? Since it's a rectangle, it should be the, how do you find the area of a rectangle?
Length times width.
Length times width. So what's the length?
AB.
AB. A times B is the length of this.
A plus B minus A.
There we go. B minus A. Okay. And what's the height of it?
H.
H. All right. And since the average value of this function is h, all we have to do is take our integral and divide it by b minus a. Or oftentimes we'll write it as this, 1 over b minus a constant out in front of the integral from a to b of f of x dx. And that's all the mean value theorem for integrals is. The mean value, the average value of a continuous function is 1 over b minus a, so 1 over the length of the interval, times the integral from a to b of the function. This is the mean value theorem for integrals. Right. There it is again. Right. So it has to be for a continuous function. Like I said, this is the mean value theorem for a continuous function from A to B. Easy enough?
Yep.
Do we have these notes posted somewhere?
Yeah, they're up now. I forgot to post them until like 10 minutes before class.
Okay, thank you.
Because I turned on my laptop and then realized that I didn't actually get around to teaching this during the first quarter, so I didn't have those notes already up there. So they're up there. And then there's another one also up there that's called accumulation and net change, I think, which we'll probably do after this if you're trying to like print them as we talk or something, or look at them or open them or whatever. I'll have tomorrow's notes up more proactively, I guess. I'll have them up. They'll be up there earlier. Okay, so what we want to do then is we want to find the average value of 4 minus x squared on the interval from 0 to 3. And then we want to figure out if x actually, or if our function f actually hits that value somewhere on the interval, and it should, it better. So if we want to find the average value on this interval for this function, first thing we need to know is the function continuous from 0 to 3? So is f continuous on 0 to 3?
Yes, because polynomial.
Because polynomial, that's right. Continuous because polynomial. All right, so now in order to find the average value of it, all we have to do is do 1 over b minus a times the integral from a to b of the function. And this should be very easy. We should be able to integrate that. We should have a constant of 1/3 out in front. What's the integral of 4? What's the integral of 4?
4.
No.
4x.
4x.
X, yeah. And what's the integral of minus x squared? Should be minus
X cubed over 3.
cubed over 3. And we'll evaluate that from 0 to 3. And that's all we need to do to figure out what the average value is. So it's 1/3 of we plug in 3, that's 12 minus 27 thirds, or 12 minus 9, minus 0 minus 0. And so what is the average value of this function from 0 to 3? Looks like it's a third of 12 minus 9, which is 1. Everybody good with that?
Yes.
Cool. And so then the second part of this question is, does our function f actually take on this value somewhere on the interval? So how would we determine if our function equals 1? Well, we just set our function f of x, which is 4 minus x squared, equal to 1. And what does that give us? It gives us x squared equals what? Should be x squared equals this is
3.
Yeah, okay, I was gonna say this is a very simple algebra. X squared equals 3, which gives us x equals plus or minus root 3. And so what's the answer to our question? Does our function actually take out in this value some point in the given interval? Should be yes, at x equals the positive square root of 3, right? Because negative square root of 3 is not on that interval. Good or no?
Yeah.
Cool. All right, let's see if we can do this one. Let's verify the mean value theorem for integrals and find all values c in which it obtains this value. So how will we find this average value? What should we start with?
Figuring out the domain.
All right, first off, yeah, the domain of 1 over x. Y is continuous. Is it continuous on, let's see, negative infinity to 0? Right? I don't know why I put a bracket there. And 0 to infinity. Right? So yes, it's continuous on e to 2e, right? Because we know its domain is negative infinity to 0, 0 to infinity. So definitely continuous from e to 2e. And then what?
Write our integral.
Okay, and what goes in front of our integral? 1 over
2e minus e.
2e minus e. And then the integral will be e to 2e of 1 over x dx. And what's 2e minus e?
E.
Okay, 1 over e. And then what's the integral of 1 over x?
Natural log of absolute value of x.
Natural log absolute value of x from e to 2e. Everybody good there? So then we'll just plug in our 2e and our e. So we got 1 over e times natural log of 2e minus natural log of e. And what's the natural log of 2e?
The natural log of 2 plus 1.
Natural log of 2 plus 1. And then what's natural log of e? That should be minus
1.
1. So we just end up with the natural log of 2 over e. So between e and 2e, the average value of this function is natural log of 2 over e. Good enough? Everyone feel okay about that?
Yeah.
All right, and then we want all values at which our function obtains this value. So we'll just make this our y value. We'll say y equals 1 over x equals natural log of 2 over e. And so at what x value do we obtain natural log of 2 over e? We'll say at x equals what? Should be, if you cross multiply, what do you get?
E over the natural log of 2.
E over natural log of 2. Good?
Good.
All right. We'll do one more of these, and this one we're going to go back to first grade for again. And we can't do a perfect job of getting the average temperature, but we can do a better job than we did in first grade. So we got some person that measured the temperature every hour from midnight, and no, sorry, from noon to midnight, and made a table of all the values. Okay. And if you were back in elementary school, what would you do to find the average temperature? You'd add 63 plus 65 plus 66 and so on till you got down to the 55. And you add them all together and you divide by, looks like 13, because you had 13 data points. And you get some number, right? And you would have said that's the average temperature. But really, that's not the average temperature, because what we need to do is we need to recognize that there aren't just hourly increments of what the temperature is, but the temperature is increasing from 63 to 65 during this hour, slightly, and then slightly increasing, and then slightly increasing more, and then slightly increasing more, and then going down slightly. That last piece was supposed to go down, right? And then going down, and then going down a little more, and then going flat, and then going down and down and down, 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 right? We have more like a continuous function here of the temperature. And so we should be able to get a more accurate representation of what the actual average temperature was during this time period. Now, if we had a function to exactly replicate this, then we'd get a really, really good answer. But since we don't, we can only approximate it by pretending that these are connected using straight lines, and we can approximate it using the trapezoidal rule. Or we could use any rule for that matter, but we'll use the trapezoidal rule. So if we want the average temperature from, we'll call it 0 to 12, right? We'll call this 0 and we'll call this 12. What should we do in front of our integral sign? Should be 1 over
12.
minus 0, right? Yep. So it's 112. And then we'll have an integral from 0 to 12 of, we'll call it the temperature function, capital T of x, dx. And we're going to approximate the integral using the trapezoidal rule. And this is something that might get asked of you on the AP test, something like this, where it would be like, hey, approximate the average temperature of this continuous function using the trapezoidal rule, or using the left Riemann sum, or using, you know, whatever they might ask you to approximate using. So we'll say 1/12, and then what do we have to multiply at the beginning for our trapezoidal rule? I know you thought we were done with that forever, but we're not. The beginning of the trapezoidal rule is b minus a over n, right? B minus a over the number of subintervals, which is 12, divided by 2. And then what goes in the first spot here?
The temperature at n.
Okay, which will be 63. And then what goes next?
2 times the temperature at 1.
All right, plus 2 times the next one, and so on. So we get to 2 times the second to last one, and then 1 times the very last one. So we end up with 1/24th of whatever this comes out to be. And I'm sure you've all been furiously typing it into your calculators already, right? So what do you get when you do that?
I got 59.5.
That's exactly what I got. So 59.5 degrees would be our average temperature throughout the day. Good or no?
Where did the 2 come from in the bottom line in front of the 1/12?
Right here?
Yeah.
It's h over 2 for the beginning of the trapezoidal rule,
Oh, that's
which is b minus a over n over 2.
Thank you.
Yep. All right. Cool. Very good. So, any questions on that? That's the mean value theorem for integrals. You'll have a short assignment tonight on the mean value theorem for integrals. And then we're also going to talk today about accumulation functions and net change. And we're going to get into a little bit about motion problems also. And we'll see, we may even get into another little topic right after this too. We'll see how things are going today. But everybody feel okay so far about the mean value theorem stuff?
Yeah.
Okay. All right, so we're going to do a couple little word problems here. We've got from 1970 to 1980, the rate of potato consumption in some country is given by this function 2.2 plus 1.1 to the t power millions of bushels per year. And t is years since the beginning of 1970. And we want to know how many bushels were consumed from the beginning of 1972 to the end of 1973. So this is what we call an accumulator function, where it tells us how many of something was consumed or used or flowed into something or evaporated from or whatever, starting at a certain time, going however far we feel like going into the future. So in this case, our function is good for 1970 to 1980. So if we want to figure out how many bushels were consumed from the beginning of 72 to the end of 73, and we are given a function that represents the rate, right? This is a rate function, millions of bushels per year. Okay. The integral of a rate function always equals an amount. Okay. We'll even say an amount accumulated. Okay, so the integral of a rate function always equals the amount accumulated. And so that's exactly what we want to do here, is we want to integrate this rate function on the correct time period. And so if t equals 0 is the beginning of 1970, what would the beginning of 1972 be? And what would the end of 73 be?
3.
No.
4.
4. That'd be the end of 73 is the beginning of 74, right? So we'll integrate this rate function from 2 to 4. And this should be the number of bushels of potatoes in terms of millions of bushels that were consumed between 1970, the beginning of 72 and the end of 73. So during that 2-year time period. So anytime you were given a rate function and asked for an amount, you just need to integrate. And what we're going to do is we're going to use our graphing calculators really quickly to integrate this. And so you should be able to, you should have your graphing calculator somewhere nearby. Yeah, everybody got their graphing calculator somewhere nearby?
Yep.
Okay, cool. Obviously, we could integrate this. Well, actually, we didn't talk about how to integrate a to the x, so we won't worry about that. But what you need to do is you need to hit the math button on your graphing calculator. And then I want to say it is option number 9 on the majority of the graphing calculators that you will all have. It should say something like FNINT. I think it looks like this, FNINT. Yeah? Or it may just look like an integral, depending on how new or old your calculator might be. Right? It may just look like an integral. Any of you have it looking like this, FNINT?
Yeah.
Yes.
Okay. Now, when you hit enter on it, does it pop up an integral or does it pop up a thing that says FNINT parenthesis?
Integral.
Integral.
Okay. Does anybody's pop up where it still says this after you hit enter on it?
Mine does.
Okay. So I'm going to tell everybody else what to do first, and then I'm going to tell you what you need to do. Whoever that was, who said that?
Cool.
Okay. All right. So for everybody else where it just pops up an integral, should be pretty easy. Just put in the lower limit is 2, the upper limit is 4, type in your function, and you'll just use an x for the t, and then put a dx at the end of it. Okay. So that's what everybody else should do. And if yours just pops up still saying FNINT, what you need to do is you need to first type the function. So you'll type 2.2 plus 1.1 to the x. And I'll write it down here, FNINT. This is exactly what you should type. 2.2 plus 1.1 to the t, or to the x, comma, x, comma, lower limit, comma, upper limit, close your parentheses. And what do you guys get for that integral?
$7.066.
7.066 millions of bushels per year. And don't forget units on this. Or sorry, not millions of bushels per year, just millions of bushels. That's bad by me. Millions of bushels. That's how many were consumed from t equals 2 to t equals 4. And whoever was telling me that theirs needed to be typed in this way, did you get the same thing?
I can't find like an X on my calculator for some reason.
You have a TI-83 plus probably is my guess.
Yeah.
Okay, I don't have mine sitting right in front of me, but it should be towards the top left-ish, I believe. It's got like an X, comma, a T, comma, a theta written on the button, I believe.
see. All right, thank you.
Depending on what setting your calculator is in, it'll either choose
Yeah, all right, thank you.
the right one. Yep. So let me know if you got 7.066 when you do that.
Yeah, I did.
Perfect. All right, hopefully you all got that. Any issues there? Everyone's good? Cool. All right, let's do another one. So we've got a pump that is connected to a generator And that generator operates at a varying rate depending on how much power is being drawn from the generator to do other stuff. So we are given the rate in gallons per minute at which our pump is operating every 5 minutes. We want to know how many gallons were pumped during the hour given to us. So thoughts on what we should do here?
Devise a function and then use an integral of that.
All right, say the first part of what you said again.
We need to write a function for the equation, or write a function for the problem.
All right, it'd be really cool if we could get a function for this, right? But unfortunately, all we're given is a bunch of data points. So we're going to have to use one of our approximation methods to figure out the integral part of it. So our integral is going to be from 0 to 60 of, let's just call it the rate function, r of t dt. And unfortunately, like you were saying, it'd be nice to have a function for this. We're going to say there is no specific function. So what method do you guys want to use to approximate it? I would think the trapezoidal would be the best. What do you guys think?
Perfect.
All right, so we'll approximate that using trapezoidal. And what needs to go out in front of it? Anything?
H over 2.
Yeah, for our trapezoidal rule, but nothing out here, right? Because we're not looking for an average, we're just looking for a total number that we're pumping, right? So nothing needs to go out in front other than just approximating this using the trapezoidal rule, which will be b minus a. So 60 minus 0 over the number of subintervals. How many subintervals do we have here?
12.
Should have 12 divided by 2, right? B minus a over n divided by 2, and then it should be 58, and then 2 times 60, 2 times 65, all the way up to 2 times that 63, and then plus 63 for the very last one. Simple enough.
Yeah.
All right, so all you're going to do is figure out what that is. What'd you guys get?
$3,582.5.
Say it again, 3,000 what?
582.5.
Does that sound good to everybody?
Yeah.
All right. Seems reasonable too, because it looks like we were doing around 60 gallons per minute, right? Each time, somewhere in that vicinity, for each time interval. And so if we did about 60 gallons per minute for 60 minutes, that should be about 60 times 60, which is 3,600. And we were pretty darn close to that. Good or no?
Good.
Let's take a look at another one. So I'll give you guys a second to read through this one, and then if you guys want to, I think maybe it'd be good to try and set it up on your own. These are getting into sort of a little bit of what you might see in some of the free response. Like this would be a very easy part of a free response question. So. Give you guys a couple minutes to read it and see if you can set it up.